Welcome to the course on VLSI Physical Design with Timing Analysis. In this lecture, we will discuss about the timing library that is used in standard cells in standard cell library. So, the content of this lecture includes timing library, and we will also discuss about the characterization of the cells in the standard cell library. So, basically if you look into the timing library, it is also popularly known as dot leaves are the logical library. Okay. Since why it is called logical library? It is basically has no basically gate level information inside that, but it has the timing and power information was in basically stored inside this file. How we can get those basically data? Through gate level spice simulation. Okay. The timing or the logical library is derived from gate level spice simulation. So, this file contains has some inside that file there are many sections are there. One is called library group, first one is the library group, then the second one is called the library label attributes, the third one is called the environment description, then the fourth one is called cell description. So, then we will discuss one at a time. First we will discuss about the library group. So, if you can see here, the library group specifies the name of the library, okay, specifies the name of the library within the scope or curly braces. So, if you can see here, this is the library name, okay, and this is the curly braces, okay, and inside that we have all the informations are stored inside this file. So, this x25 is the library name. Anything between this curly braces is part of this entire library group. Okay. So, anything between these curly braces are a part of the entire library group. Usual practice is that keep the name of the file same as the library name. Okay. So, in this case this file name should be ex25.lib. Okay, ex25.lib. So, if you can look into this one, it has some basically parameters are there. Okay. So, this it has first we have library group, then we have library label attributes. Okay. So, the second one is the library label attributes are the statements that apply to the whole library. Okay. There are some statements there inside this library group, and those are applicable for the whole library. So, the library label attributes, what are the things it contain? The first one is the technology name, units and date, and the second one is called is the default value of the parameter such as input output pin capacitance, then the max fan out, max transition time, etc., etc. If you can see here, you have a CMOS process, a technology name. Then the delay model type is table underscore lookup. Okay. So, it is a table lookup model is used here. Then the date when it is created and a revision when it is updated. Then we have some parameter like current is measured in ampere, the time is measured in nanosecond, then the voltage is measured in 1 volt, and the pulling resistance is measured in terms of 1 kilo ohm. And there are some default parameters are given here, okay, and the capacitance whatever the capacitance is there, it is measured in picofarad. So, now we will go into the environmental description part of the library. So, we discussed about the library group, we discussed about library label attributes. These are the variables and what is its value. The basically these are various parameters, you can say parameters and its corresponding values. Then the third one is your environmental description. So, this environmental description is used basically to model at different conditions. Okay. So, it is used to model the variation in process is one thing, then the voltage and temperature, that stands for PVT. So, if you change the process, then your timing values will change. If you change the voltage, your timing will change, your temperature, your timing will change. Why you need all these? Because let us say I use a smartphone. The smartphone, let us say it is, if you are using it for a longer period, it will heat up. Okay. Once it is heat up, then the behavior of the delay inside the chips will be different. Okay. So, what happens is that whenever you design the chip, we need to make sure that our smartphone should work at different temperature. Whenever, even if it is heated up, still it should work. Okay. Because of activity factor, if the temperature goes up, still it should work. So, we need to simulate our design across worst case process, worst case voltage and worst case temperature condition, such that the system should not fail in any extraordinary conditions. So, it also contains a scaling factor. It is like a multipliers, then the operating conditions, then the third one is the wear load models. So, the scaling factor are basically k factors are the multipliers. Okay. So, those are the multipliers. So, what it does is that it will either increase or decrease. Derate means that either increase or decrease the value based on different process voltage and temperature conditions. Okay. So, here if you can see, some of the k process fault transition is 1. So, the k process rise transition is 1.2. So, whatever the value of rise transition will be there, that will be multiplied by 1.2. So, similarly for other parameters it was written here. Okay. So, it is a multiplier, with the actual value will be multiplied with this k value to find out the worst case condition inside that circuit. So, now we will discuss about operating conditions. So, we have basically operating conditions specify the process, voltage, temperature and RC tree. So, if you can see here, your process is 1, because this is a nominal or typical process, this is also called typical. Okay. So, the process is 1. Okay. Now, temperature is a nominal temperature, the room temperature 25 degree. Okay. Now, your voltage it is 3 volt. Then the RC tree, that interconnect model is balanced tree model is used here in this particular example. Okay. There might be different process condition, temperature condition, voltage condition and RC models can be used to mention the operating conditions of your dot leaves. So, now what happens is that where we will use these things? You will use these things in basically logic synthesis, physical synthesis and timing analysis. So, these operating conditions are used in synthesis phase and during timing analysis phase. Okay, because I want to simulate our design at worst case conditions. So, I need to use those dot leaf files in logic synthesis, physical synthesis and timing analysis tools. Then the tree type is basically a attribute to model the interconnect or the wires. Now, we will discuss about the that interconnect model, which is stored as wear load models actually. Okay. So, this is stored as wear load model. If you can see here, this is the wear load. Okay. Then here there is a wear load model is specified here. So, in this one, what we are doing is that we are estimating the wear length. So, we are designing a chip, we need to pre-estimate the wear length and it is used during the pre-layout phase or logic synthesis phase. Whenever the layout has not been done, we can use this wear load model to estimate how much delay can be possible due to the wear loads, So, that will help us to predict that much of basically slowdown of the delay can be possible in the final layout. So, we can budget for that one. So, what it contains? It contains capacitance, resistance, third one is the area factor, then the fourth one is the slope, then the fifth one is the fan out length. These are the information will be used by the tools to find out the effective delay through the interconnect, and that will add with the actual gate delay to estimate the overall critical path delay of the actual design. So, now then there is another section is there inside the dot lib, that was the cell description or the cell groups. What it contains? It contains pin groups, R group informations, attributes. So, it has also capacitance value for input pin, it has capacitance information for input pin and output pin also. Then whenever you have basically input pins, if you have an input pin, for that one what is the fan out load, that will be specified. So, if you can see here that input pin, this is a I is a input pin for this buffer, then the fan out load is mentioned to be 2 here. Then you have max transition time for the input pin. So, it can be mentioned for either input or output pin, max transition time can be given for both of them. Then you have max capacitance can be given for output or in out pins. Those informations are need to be captured as cell description. Now, I will give an example how this tool will utilize that information. Let us say in this basically cell description part, we have basically the max fan out of the Z pin is 4, max fan out of the Z pin is the 4, okay, corresponds to this one. Then you have fan out load, the fan out load is 2. So, the fan out load here is the 2. So, in this case I have this buffer, I have a buffer is there, then what tool will do that, how many load it is driving. So, if you can see here that the output pin has a maximum fan out of 4 and the input input fan out load is 2. So, it can drive 2 similar kind of buffers, 2 similar kind of buffers. Okay. So, if I have a requirement of driving more than 2 buff cells, then I need to modify this buffer cell, because this buffer cannot drive more than 2 same type of buffer, This kind of analysis will be done by the tool. So, now what I will discuss about, let us say you have a basically combinational cells. Okay. How do you characterize and what are the parameters for the combinational cells will be stored inside a dot lib. Let us say I will take a example for a inverter. Okay. So, in general I will discuss first, then I will discuss about the inverter. For each gate, for each logic gate in standard cell library, okay, I have 2 parameters stored there. Okay, one is delay, propagation delay, the delay of the logic gate, D. Okay. So, that is basically a function of 2 things. Let us say I have a inverter, the delay of an inverter is depends upon 2 parameters. Delay of the inverter will depend upon 2 parameters. One is the output load and input slew. This is the input slew. The 10% to 90% or 20% to the 80% of the input signal. Okay. It is a function of, let us say this is CL and let us say this is S in, rise, S in. In general I am writing first in general, then I will go to the particular case or the special case. So, here the S in comma CL is a function of S in and comma CL. So, this S in is basically your is the input slew or input transition time, then the CL is your output load. Load capacitance. So, now we have two types of delay, one is rise propagation delay. So, one is rise propagation delay, then the B is fall propagation delay. Okay. So, now this is the case, then let us say then the second case, okay. Second case is that output transition time. Of the gate. So, what is happening here? The output transition time is S out is equals to is also a function of same S in comma C L, is a function of S in comma C L. Now, what it has also two types of transition, one is called rise output transition time. So, rise transition time, okay, output rise transition time, then the B is output fall transition time. So, I have two things here, one is S out, I have delay, correct. So, now I have 4 parameter for a logic gate. Okay. So, now I will consider the delay of the inverter for inverter. Okay. If it is an inverter, then what happens, my I have 4 parameters here. Okay. So, I have 4 parameters. Okay. Your rise propagation delay, let us say I will denote by DINV rise, DINV fall. Okay. Now, output fall transition time I will denote by S out rise, S out fall. Now, I have to be very specific. If I consider a inverter, okay, my D rise, the first one A D INV rise is a function of CL comma S in fall, because my output rise propagation delay will depend upon the fall transition time. Why? Because let us say I am output is why this is the case, let us say my delay whenever I am defining, let us say this is my input, let us say this is input, this is in and this is out. Okay. So, here this is my rise delay, this is my rise delay. So, if this rise delay will depend upon the fall slew. Okay. So, similarly your so D rise inverter is a function of S in fall. Okay. So, it is a depend upon the fall slew. Similarly, if I can say D INV of fall will be a function of output load comma S in rise. Okay. So, this is for 1B, so this parameter. Similarly, 2A is this parameter, it is S out rise is a function of f of CL comma S in fall. The rise slew will depend upon the input fall slew. Similarly, to B S out fall will depend upon CL comma S in rise, correct. So, these are the things why it is essential. Let us say if I are doing library characterization, you need to use those value. Let us say I want to use the rise propagation delay, I will change my CL and SIN, so that my rise propagation delay will be found out for different output load and input slew conditions. Similarly, for all other cases. So, now then there is a question arises, I am interested about the delay, why I am looking for the output transition time. Okay. Since I am looking for the delay, why I am worried about the output transition time. Let us say I have a chain of gates, let us say I have a inverter AND gate OR gate like this. So, let us say I am interested about the delay of this gate, why I am finding the output transition time. So, this is my question. The question answer is that since I found out the delay of this gate based on the input transition time and output load at this point, I need, whenever I am finding the delay of this AND gate, I need the input slew at this point, That input slew can be calculated from the table dot-lib tables, from the inverter dot-lib tables. Okay. So, that will be used by the timing analysis tools. That is the reason we are storing the output transition time along with the propagation delay. So, for inverter, how many tables should be stored? So, here basically delay parameters corresponding to the inverter. What we are doing here is that we have we are varying the load and slew. Okay. So, one is the load, one is the slew, the index, these are the index. So, those are varied for different combinations are plotted here, stored here. Okay. So, these are the delay values. This is the fall propagation delay, this is the fall propagation delay, and this is the fall transition time, this is the fall transition time. Okay. This is a fall transition time. Similarly, there is a basically this is rise propagation delay, then the rise transition time. So, for only inverter we have 4 table corresponding to the timing. Okay. For inverter I have 4 tables inside my dot-lib, inside the timing library. What are those tables? 4 tables. One is your cell rise, one is your cell fall, then you have rise transition time, then the fall transition time. So, these 4 tables are needed for only inverter. These 4 tables are needed only for inverter. Similarly, if I go to the NAND gate, so depending upon the number of arc, each arc should have 4 tables. So, if you have any logic gate is there in and the corresponding timing information need to be stored in the timing library, then the we need to find out number of arc in that logic gate, then for each arc cell rise, cell fall, rise transition time, then the fall transition time. So, basically we discussed about what are the tables inside the .lib or liberty file is there. Then the question arises, how do you create those files? These are done using spice simulation of the inverter. It is basically the transistor level simulation. Okay. It is a transistor level simulation. So, here if you can see, this is a NMOS and this is a PMOS, it is creating an inverter. So, this is the schematic of an inverter. So, then this is the spice netlist for the inverter. So, in the spice netlist, you have the this inverter information is encoded here. Then you are applying the model file, which model you are simulating here. Then you have a temperature at which temperature you are simulating. Then the supply voltage information is given here. Then you have basically input pulse you are providing here, you are providing a input pulse. Okay. So, that is given here. So, this line will create the pulse, then this is basically correspond to your supply voltage. So, now we are doing a transient simulation. So, here the transient simulation is given here. So, this is the SPICE netlist of the inverter. You have to characterize this one across different input slew and output load conditions to create those tables. Create those tables, these 4 tables for the inverter. Now, so here this is very ideal case, but let us go into little actual simulation, because your input slew inside the circuit is not linear. Here it is assuming that your input slew is basically linear. So, if you can see here, your input pulse is very straight line. Ideally, there is no slew in this simulation. So, in actual circuits, the slew is input slew is not basically linear. In actual circuit, this slew is not linear. So, in order to take that into account, what happens is that we have to shape the input slew here using 2 inverter, and we have a load which is a fan out of 4 load. This is F of 4 load placed here, and this is the SPICE netlist for calculating the fan out of 4 delay of the inverter. Okay. So, here what is the main advantage is that we are capturing the slew information, actual slew information inside the circuit, and we are modeling nonlinear slews. That is why this results will be give me the more accurate results, So, this is the basically SPICE simulation, this is the output of the SPICE simulation. You can use open source tool like LT SPICE to simulate this. Okay. You can create this schematic and simulate this and find out these delay values, and you can create use a some kind of Python script to create the dot tables and put it into your .lib file. So, this is the procedure how to generate the .lib files and using some SPICE simulation. This is related to the combinational circuits. In this lecture, we discuss about basically timing library .lib file, what is inside that timing library, and how we can generate the delay table inside the timing library using SPICE simulation. Thank you for your attention.